In 484 AD, the people of Athens looked up and watched the sun disappear. Total darkness, in the middle of the day. What they had no way of knowing is that this single moment would expose a flaw in how humans measure time itself. A flaw that scientists wouldn't even notice for over 1,000 years. I'm FactSpark. If this is your first time here, subscribe. We turn wild science into something anyone can understand, with zero fluff. Let's get into it. Around 1700, natural philosophers had built something almost magical: classical mechanics. A mathematical machine that could predict the future positions of every object in the solar system. You feed it the current position and speed of, say, the moon, and the gears turn, and out comes the exact location of that object at any moment in time, past or future. Predicting comets, discovering new planets before we'd even seen them. And here's where it gets interesting: predicting solar eclipses with complete precision. Because a solar eclipse is not simple. If you live in some village and you see one, there's no obvious way to know when the next one will hit your exact spot on Earth. Before classical mechanics, people could make educated guesses. But with it, you just run the equations, feed in the moon's position, the Earth's rotation, and the math hands you the answer, here and at this exact time. That power, that total confidence in the machine, is what led astronomers like Halley and even Kant to ask a question nobody had asked before. If we can predict eclipses in the future, why not verify ones from the past? This is where it gets really strange. And honestly, I want to ask you something right here. Think about the oldest piece of recorded history you know.
Something written down by an ancient civilization? Drop it in the comments. Because the fact that ancient records are about to crack open a problem in modern physics is exactly the kind of thing that should make you rethink what useless old history even means. Anyway, back to the story. In 1690, there had been a total solar eclipse visible from Korea. Astronomers ran the mechanics backwards, fed in the right numbers, and confirmed it perfectly. Success! The machine worked in reverse. Feeling bold, they pulled out the history books and found something older. A biography of a philosopher named Proclus described how the people of Athens witnessed a total solar eclipse on the 14th of January, 484 AD, over 1,000 years earlier. They ran the calculation, and the machine said, no, not a total eclipse. The prediction placed the path of totality nowhere near Greece. Athens should have seen only a partial eclipse, the sun dimming a little, not disappearing. But the historical record was unambiguous: total darkness, in Athens. So either the historians were lying or something was wrong with the machine. Let's rule out the obvious first. The date was actually very well documented. This wasn't some vague legend. It had been recorded in detail, so a dating error was unlikely. That left the machine itself, and when astronomers looked closely at the numbers, they noticed something peculiar. If you could magically rotate the Earth back by just 30 degrees, the predicted path of totality would fall perfectly over Greece. 30 degrees. That's it. Now, that might sound like a technical detail, a small correction, no big deal. But sit with it for a second. Either the moon used to move slightly slower than it does now,
Or the Earth used to spin slightly faster than it does now. Halley bet on the moon. He argued that the moon had been gradually accelerating over time. And you know what? He wasn't entirely wrong. But he stayed very quiet about the Earth's rotation, and that silence turned out to be hiding something enormous. Here's why this matters so much. Ask yourself, what even is a day? You look at the sun, you wait, and when it comes back to the same spot in the sky, a day has passed. One full rotation of the Earth. That rotation is divided into 24 hours, each hour into 60 minutes, each minute into 60 seconds. 86,400 seconds per day. But, and this is the key question, what if that rotation was faster in the past? Then the day was shorter, and every second, every minute, every hour was slightly smaller than the ones we use now. The ancient Greeks weren't living in the same temporal framework as us. Their second wasn't our second. Time itself, as we measured it, was different.
Now, I can already hear you thinking, okay, but how different, really? If the error was just 30 degrees across 1,500 years, the change must be tiny. And yes, it is tiny. We're talking about 2 milliseconds per century. The day gets 2 milliseconds longer every 100 years. Tiny, but not irrelevant. GPS satellites need time accurate to nanoseconds. Every piece of modern electronics, every synchronized network, every financial transaction timestamp, all of it depends on time being a fixed, reliable ruler. You cannot have a ruler that stretches. But wait, is one ancient eclipse really enough to rewrite how we think about time? Fair question. And the answer is no. It's not just one eclipse.
Researchers went back through historical records from across the world. They found records of the moon occluding, passing in front of, specific stars, going back to the 17th century. Classical mechanics could predict those too, and again, tiny discrepancies showed up in the timing. Going further back, there are eclipse records from Byzantium, from China, and from Mesopotamia, all showing the same small but consistent drift. And one of the most remarkable pieces of evidence comes from ancient Babylon, around 136 BC. An astronomer there recorded not just that an eclipse happened, but exactly where the sun was in the sky when it started, and where it was when it ended. Precise, methodical observation from 2,000 years ago. That level of detail allowed modern scientists to reconstruct, almost like detectives, how the length of the day has changed across human history. It's part astronomy, part archaeology, and it's one of the most beautiful intersections of ancient knowledge and modern science I've ever come across. So, what's actually slowing the Earth down? You might think a spinning ball slows down because of friction. Air resistance, surfaces rubbing together, energy bleeds away and the rotation fades. But the Earth spins in the vacuum of space. There's nothing to rub against. So why is it decelerating? The answer is the moon, specifically tidal forces. The moon's gravity pulls on Earth's oceans, creating a bulge of water that tries to follow the moon as the Earth rotates. But the Earth rotates faster than the moon orbits, much faster, so that bulge gets dragged ahead. It's always slightly in front of the moon's position, not perfectly aligned with it. Now that water bulge has its own gravitational pull. And since it sits slightly ahead of the moon, it tugs the moon forward, which very gradually increases the moon's speed and pushes it slightly farther from Earth. Every year, the moon moves about 3.8 centimeters further away. But there's no free lunch in physics. To give the moon energy, the Earth has to lose it. That loss shows up as a tiny but consistent slowing of Earth's rotation. That's Halley's puzzle, solved. He was half right. The moon does accelerate because the Earth feeds it energy while slowing down itself. Here's where it gets even more layered, because the Earth doesn't just smoothly decelerate, it fluctuates constantly. Look at the daily variations in Earth's rotation speed from a single recent year, and you'll see a chaotic-looking signal. The day getting longer and shorter by fractions of a millisecond, constantly shifting. What's causing all that noise? The biggest driver, accounting for roughly 90% of the variation within a single year, is the atmosphere. Air moves, pressure systems shift, massive wind patterns redistribute mass across the planet, and when mass moves closer to or further from Earth's axis, the rotation changes. Think of the classic figure skater pulling in her arms to spin faster. Same principle. Change the shape, change the speed. Below that, on timescales of decades, the main culprit becomes something we rarely think about: Earth's liquid outer core. That spinning mass of molten iron interacts with the rocky mantle above it, exchanging angular momentum in ways that are still not fully understood. The core and the mantle don't move as one. They push and pull against each other, nudging the rotation of the surface we stand on. And then there's one more factor. One that's particularly relevant right now. When glaciers formed during ice ages, their enormous weight pushed down on the land beneath them. Now, as the ice sheets in Antarctica and Greenland melt, the land underneath is slowly bouncing back. rising, redistributing mass. That redistribution changes Earth's shape, which changes how it spins, which changes the length of the day. The climate crisis isn't just about temperature and sea level. It is, quite literally, changing the pace of time. So, where does this leave us? Did we fix the problem? Yes, though it took a long time to get there. For most of history, Earth's rotation was the best clock we had. Imperfect, but stable enough that we could live with it. The problem was that stable enough isn't good enough anymore. Not when you're coordinating satellites in orbit and synchronizing networks across continents. The solution came from an unexpected place, the element cesium. Under the right conditions, cesium atoms emit light at an extraordinarily specific frequency, 9,192,631,770 oscillations per second, to be exact. And unlike the Earth's rotation, that frequency doesn't change. It doesn't matter when you measure it, it doesn't matter where. It is always, without exception, identical. So we redefined the second, not as a fraction of a day, but as exactly that number of cesium oscillations. The astronomical clock was retired. The atomic clock took over. Time became a fixed ruler again. What's remarkable about this whole story is how it started, with a historian's note about an eclipse over Athens. Not a laboratory discovery, not a cutting-edge experiment.
A line in an old biography that said, "On this day, the sun disappeared over Greece." That small historical fact, checked against the precision of mathematics, cracked open questions about the moon's orbit, the Earth's rotation, the nature of time measurement, the interior dynamics of our planet, and the long-term effects of climate on our physical world. Hipparchus discovered Earth's axial precession, that slow wobble like a spinning top, by comparing his own astronomical measurements to records made 100 years before him. The past was his data set. That Babylonian astronomer, who carefully noted the sun's position during an eclipse 2,000 years ago, had no idea that his observations would one day help physicists calibrate atomic clocks. He was just doing his job, recording what he saw. Which leaves you with a genuinely unsettling question. What are we recording today? What measurements, what observations, what data points that will mean something completely different to whoever reads them 1,000 years from now? That's the thing about science. You never fully know which piece of the puzzle you're holding. If you made it this far, subscribe to FactSpark. There's a lot more of this kind of thing coming. See you in the next one.